Hey guys, this is Sakshi back and I welcome you all to my edtech platform, Way to Learn. So we are going to solve matrices, PYQs and from CSIR-NET Physical Sciences. So let us start our problems of PYQs today. So I hope you enjoyed the last video. So let us see for more properties and more easy way to solve a problem from matrices. So today's question over here is consider a n cross n matrix. We do not know what is the order of the matrix, right? Okay. Which Aij is the product, the indices Ij. So the matrix over here, the element are like product of the indices. So I'll let you know how to write that particular matrix. And the options given here as is the matrix has one degenerate eigenvalues of degeneracy, and like we have to basically find the eigenvalues. Then we have to see is it degenerate or like is it generating again and again. Okay, and if it is generating, then like how many times is it generating? Okay, that is the degeneracy. So let us see. So now according to the question, the elements Aij is the product of the indices Ij. That is Aij is equal to I into j. So we basically write our matrices as A11, A12, A13, and so on, right? A21, A22, A23, A31, A32, A33. So basically it is a n cross n matrix, so it might like go on, but I'm going to consider over here a 3 by 3 matrix. Okay, we can consider it. It's up to you. So now let us find the elements over here. They are the product of the indices. So indices over here is 1 in 1. So 1 into 1 is 1. Then 1 into 2 is 2. 1 into 3 is 3. 2 into 1 is 2. 2 into the product of the indices is nothing but this. INJ. 2 2s are 4. 2 3s are 6. 3 1s are 3. 3 2s are 6. 3 3s are 9. So now if you see again a property arises over here. If you see this matrix has like a row is a multiple of other row, right? First row is a multiple of the other row, and the first column is also the multiple of other row, other column. So for such kind of matrices, the eigenvalue will be equal to trace, 0, 0. So now the trace over here is 14 and 0, 0. Now we have to find like what is the degeneracy and what are the degenerate values, right? So if you see, is 14 occurring again in this lambda? No, only 0 is occurring. So it has only one degenerate value, and that value is at 0. Okay, and that value is 0, right? So only one degenerate value. Just remember this. What is occurring again and again? 0 is occurring, right? So when 0 is occurring again and again, then it means that that is the one particular degenerate value. 0 is the one value which is occurring again and again. So it has only one degenerate value which is 0. And now we have to find the degeneracy, right? So degeneracy basically here is we are going to consider over here. We have already considered 3 by 3 matrix, right? So degeneracy is like how many times it has occurred. So 0 has occurred 2 times. Now, how do you relate with the order of the matrix? I can say for 3 by 3 matrix, my 0 has occurred n minus 1 times. Right? So, this is the degeneracy over here. So, now if you see the question, you can say that it has one degenerate eigenvalue which is 0 and the degeneracy is n minus 1. So, a very simple question, just words are tricky over here. You just have to know what are degenerate eigenvalues and degeneracy and how do you relate them to your matrix. Next is a very simple question. I think you can even solve this. a very simple question. You have three matrices A, B, and C. You have to see which satisfy the commutation relation. So basically in here you see that you have to find A comma B and B comma C. So if you find only those two, it is easy for you to answer the question. So let us find A comma B. So how do you write A comma B? A comma B is AB minus BA. So now I have to find A into B and B into A. Right. So now I'm going to find AB, which is, so on multiplication I get 0, 0, 0, 0, 0, 1, and okay. So this is equal to C. If you see the matrix C, it is of the same form. Now we have to find BA. So on doing the product over here, you get all the elements over here are 0, 0, 0, which is 0. So the commutation relation of A comma B will give you C minus 0, which is equal to C. Okay. So now we have to find the other commutation relation, which is B comma C. You can write that as BC minus CB. So now when you find BC, okay, now when you find BC, it is going to be equal to 0, and CB is also going to be 0. So you have to find the product, right? So after finding the product and applying this in your commutation relation, you get 0 minus 0, which is 0. So now A comma B commutation relation gives you C, and B comma C gives you 0. So the only option that satisfies this is option D. If you want, you can find C comma A, you will get B. So let us see the next problem. Here the matrix is given and the eigen, we have to find the eigenvalue. So basically we are not going to use the Cayley-Hamilton theorem because it is going to take a longer time for you to solve. So now here we are going to use the properties. So the trace of the matrix will give you which is equal to lambda 1 plus lambda 2 plus lambda 3. Right. So now the trace of the matrix will be 0, 0 plus 0 plus 0, which is 0. Okay. Now we have to see which option satisfies. So 2, 3, 6, this does not satisfy. So this is not the eigenvalue. This satisfies, and this also satisfies. So now we have to find the determinant. Okay. Now after finding the determinant, 0 into anything will be 0. Then 2y into 0 plus 89. So this is plus 36. Okay. So if you see, your determinant m will be equal to 0. So now you have to find which condition satisfies your determinant condition. Okay. Uh, I now you have to find which satisfies. So your product, that is determinant m, should be equal to product of the eigenvalues. So now multiplying the eigenvalues, you get this is not equal to 0, this is equal to 0, and this is not equal to 0. Hence the only option that satisfies is option B. So it's very easy over here. So next let us see our ninth problem. So you have given a unitary matrix which satisfies the unitary matrix condition, and we have also given that determinant of u is e power I phi, and you have given it as a 2 by 2 unitary matrix. So using that unitary matrix, one has to construct a unitary matrix V. Using that u, whose determinant is e power I phi, we have to construct a other unitary matrix which is V, and whose determinant should be equal to 1. So how do we construct such matrix? So here they have already given in the options that you can multiply that particular u by e power minus I phi by 2, or e power minus I phi, or multiply rho by e power minus I phi by 2, and so on. So you have to choose one of the options, and then you have to try, okay, I'm going to do this and I'm going to get this value. So let us solve this. So we have a 2 by 2 matrix, unitary matrix u. So we have a unitary matrix U, which is a 2 by 2 matrix. We do not know the elements, so I am going to consider this as A, B, C, D. And I know that that of U is e power I phi. So I can write that AD minus BC will give me e power I phi. Right? I have just found the determinant. This is going to give me e power I phi. Now, based on the option, I am going to choose my first option. I have to construct a matrix V. So I'm going to use option A, multiplying u by e power minus I phi by 2. So I have to multiply all the elements A into A, B, C, and D with e power minus I phi by 2. So that will give me my new matrix, right, according to the option. So e power minus I phi by 2 into A, e power minus I phi by 2 into B, e power minus I phi by 2 into C, e power minus I phi by 2 into D. And I also know that determinant of V is equal to 1. So I have to use this condition over here, and I have to find if I am going to get the determinant equal to 1 or not. So when I multiply this, e power minus I phi by 2 A into e power minus I phi by 2 into D minus, okay, so it's B. Okay. Now on doing that, I am going to get e power minus I phi by 2 into e power minus I phi by 2 is nothing but e power minus I phi. AD minus e power minus I phi CB. So I can take this e power minus I phi as common and write this as AD minus CB. Okay, this is nothing but the determinant. So I have to get this determinant value equal to 1. Now this is the last value that is simplified over here. Now if you see this thing, AD minus BC is e power I phi. So I am going to use this AD minus CB as e power I phi. So I get e power minus I phi dot e power I phi, which is equal to e power 0, which is equal to 1. Hence the determinant will be 1. So on multiplying u with e power minus I phi by 2, I am going to construct a new matrix V. So this option A satisfies. If you want to find using option B, option C, and option D, you can also find. You can see if it is satisfying this condition or not. So let us see the last question of the day. Here the column vector is given, and which is the eigenvector of this A and B. If so, when does this particular vector becomes an eigenvector of A and B as well? So we have to find which condition helps it to become a eigenvector. So now basically if we have to find an eigenvector, uh, we use Cayley-Hamilton theorem, find the eigenvalues, and then do all like ax, like, okay, just see this, ax is equal to lambda 1x. So this is basically the step followed in order to find the eigenvector. So here x is the eigenvector. So I'm going to use this. Here x1 is for a, and bx2 is equal to lambda 2 x2 is for b. I'm not going to use Cayley-Hamilton theorem to find the eigenvalues and all. I'm just going to directly substitute in this formula. So let me substitute over here for a vector. A is 0, 0, 1, 0, 1, 0, 1, 0, 0 into x. What is the eigenvector over here? A, B, A. And I don't know my lambda, so I'm going to consider it as lambda 1, A, B, and A. So on solving this equation, you're going to basically get as A is equal to lambda 1 A, B is equal to lambda 1 B, C, okay, again A is equal to lambda 1 A. So if you see, you get lambda 1 is equal to A from all these equations. Sorry, lambda 1 is equal to 1 from all these equations. So you do not get any information about A and B. So we are going to basically use the other equation, which is Bx2 is equal to lambda 2 x2. So over here our B is 0, 1, 1, 1, 0, 1, 1, 1, 0. A, B, A, which is equal to lambda 2 A, B, A. So the three equation found over here is B plus A is equal to lambda 2A, A plus A is equal to lambda 2B, and A plus B is equal to lambda 2A. So using the second equation, I can say that lambda 2 is equal to B by 2A. Now in this lambda 2, I have something about my B and A, right? So I'm going to use this lambda 2 in one of the equations, first and third, and I'm going to find the relation between A and B. So I'm going to use the first equation, which is B plus A is equal to B by 2A into A. Sorry, this is 2A by B. Lambda 2 will be 2A by B. So I'm going to use this over here. So I get 2A square in equation 1. So 2A square by B, which will give me B square plus AB. So this is a quadratic equation. Now I have to simplify this quadratic equation. So I'm going to just make this 2A as a common number. Okay, first let me write this. I'm going to split this as minus 2AB plus AB minus B square. So now I'm going to write this 2A as A minus B plus. So now I can write this A minus B is equal to 0 and 2A plus B is equal to 0. Now A will be equal to B and B will be equal to minus 2A. So now we have to see which option satisfies. So I think option B satisfies. So I hope you get all these problems. So we have completed around 10 problems from matrices. So there are only a few more problems remaining. So we are going to see all the problems in my upcoming videos. So stay tuned for my upcoming videos, and thank you. Like my videos and share my videos if you find it useful, and subscribe my channel, and also do not forget to hit the bell. So see you tomorrow. Ta-da!